Okay, so let me teach you how to predict whether a molecule is polar or not. So there is a flow chart to follow when you're predicting whether something is going to be polar or not. And what I think I will do is I'm going to write it in this blank here on the left-hand side, and then you guys can just copy it down. Okay, so the first question is going to be, is a polar bond present? If the answer is no, then it is automatically a non-polar molecule. And what is the polar bond range? 0.4 plus, basically. Okay. All right. And then if the answer here is yes, then you have to ask yourself, is the shape symmetrical? And there are a few different symmetrical shapes. They are listed in your book, but I will give them to you here. So that means you're looking to see if it's linear, trigonal planar, tetrahedral, or octahedral, trigonal bipyramidal, and square planar. Okay. If the answer here is no, then it's a polar molecule. And that's because in symmetrical shapes, the bond dipoles, which come from polar bonds, they will not cancel if it's not a symmetrical shape. So if it's like tetrahedral, trigonal pyramidal. Trigonal pyramidal is not symmetrical, so the bond dipoles will not cancel. That's why it's a polar molecule, because it throws the electron distribution off. If the answer here is yes, it's a symmetrical shape, then you have one last question to ask. Are the bonded groups the same? Are the bonded atoms the same? Okay. So if the answer here is no, then it's a polar molecule. And if the answer here is yes, then it's a non-polar molecule. Okay, and I'm going to explain this as we go through a few different types of molecules, so it makes sense to you, okay?
The bonded groups have the same electronegativity.
Then it would be a non-polar bond, probably. It depends on the bond type. I'll show you what I'm talking about. Okay, are we ready? Yeah. Okay. In your lab, you start out with some just bonds, right? Like you have an HCl bond, you have an ICl bond, you have a Br bond. When you just have a bond, just calculate the difference in electronegativity. And then from there, if it's a polar bond, call it a polar molecule. Does that make sense? So when you are looking at the lab and you're filling in the polar bond present column, you should write down each type of bond that exists in the molecule, and you should calculate the electronegativity difference there, and then answer whether you have a polar bond present or not. And then you can go to the last column, which asks if it's a polar or non-polar molecule. So let me give you an example. If we come down here and we're looking at HCl, this is just an HCl bond. I would look at the electronegativity values. Can I borrow this for a second? So H is 2.1, I believe, and then Cl is 3.0. So what you would do in the polar bond present column is I would write HCl, and then I would take 3 minus 2.1, which is 0.9, and then you would say, yes, it's a polar bond. Okay, and then you can jump, since all you have is a bond, you can jump straight to the polar or non-polar molecule column, and you'd put a yes. It's a polar molecule. Okay, because it doesn't matter. We don't have the same atoms bonded to each other, so therefore the bond dipole doesn't cancel. Does that sort of make sense? You only have to consider the one single bond when it's a bond, okay? But if it's more complicated than that, so if you turn to the next page, and we take a look at carbon dioxide and water as an example. When it's more complicated than that, you need to consider the fact that you might have multiple bonds. So here in carbon dioxide, I've got carbon, which is, what does that say, 2.5? And then oxygen, what did I say, is 3.0? 3.5? Okay, so here I've got a carbon double bonded to oxygen. I've got two of them. Calculate the difference in electronegativity here, which is going to be 3.5 minus 2.5, which is 1. This is a polar bond. Agreed? Okay, so yes, you have a polar bond. You go to the next question. Is this a symmetrical shape? Well, this is AX2. So this is linear. Is linear a symmetrical shape? Yes. Are the same atoms bonded to the central atom? Yes, they are. So what that means is this bond dipole here and this bond dipole here, which comes from polar bonds having unequal sharing of electrons, the bond dipole cancels because linear is a symmetrical shape and I have the same atoms bonded to the central atom, and that makes this a non-polar molecule. Okay, when I take a look at water, water's a little bit different. I'm going to draw water so it looks like this. Okay, oxygen is 3.5, hydrogen is 2.1. The only bond I have here is an oxygen-hydrogen bond. I have two of them. The difference in electronegativity here is 3.5 minus 2.1. What's that going to be? 1.4? Okay, this falls within the polar bond range. So then I can go to the next question in the flow chart, which is this a symmetrical shape? This is AX2E2. This is bent. Bent is not a symmetrical shape. That means the bond dipoles don't cancel out. What you'll often see them do with water is they will draw water with the dots on top, and it'll look like this. You've got arrows pointing towards the oxygen because it's more electronegative. These bond dipoles do not cancel because bent is not a symmetrical shape. So that's why this is a polar molecule. Okay? Let's take a look at two more examples. Let's come down here to CCl4, so carbon tetrachloride, okay? In carbon tetrachloride, chlorine is more electronegative than carbon. It's a polar bond. So this carbon-chlorine bond is polar, okay? You can see the bond dipoles drawn in there. And this is tetrahedral because it is AX4. Tetrahedral is a symmetrical shape. And all of the atoms bonded to the central atom are the same. That means the bond dipoles will cancel and we get a non-polar molecule. Okay, because there would be equal sharing of an equal distribution of electrons. Over here, this is CH3Cl. I have two different types of bonds here. I have a CH bond and a CCl bond. Okay, so you would want to calculate the difference in electronegativity for both to determine if one of them is polar. Both of them are polar bonds. Okay, you can see how the electrons are distributed by the bond dipoles that are drawn in. Yes, this is tetrahedral because it is AX4. And I don't have the same atoms bond with the central atom. I've got chlorine here, and then I've got 3 hydrogens here. So that means the bond dipoles can't cancel, and that's why this is a polar bond. Okay? Okay, let's take a look at... was this a good summary for you? Do you understand this, or do I need to kind of like do a little bit more? No comment. We're good? Okay.